In 5.2, we're going to focus on the exponential aspect. We focused on the natural log aspect in 5.1. Now we're going to focus on how do we actually integrate exponential functions, e to the x, 2 to the x. How do we integrate with that? So as a warm-up, let's actually review what we did in 5.1 and use logarithmic differentiation to find the derivative of y equals e to the x. So go ahead and pause the video, take the natural log of both sides, figure out what you get for that derivative, and then unpause the video and see how you did. So the very first thing I'm going to do is I'm going to take the natural log of both sides. So natural log of y equals x natural log of e. Then I'm going to take the derivative of both sides with respect to x. So this is going to give me 1 over y dy dx equals, well, natural log of e is just 1, so this whole thing just simplifies to be x, and then when I take the derivative of that, I just get 1. So now let's multiply both sides by y so that I can have dy dx isolated. So I'm going to get that dy dx is y. And y, going back to the beginning of this problem, y was just e to the x. So we just said, this is really weird, and I think you should stop and kind of think back and look at what we just said. What we just said was the derivative of y equals e to the x, or the derivative of e to the x is e to the x. And that is very, very unique. And it's so unique that this is actually the only function whose derivative is itself. Now, there are other ways to prove that the derivative of e to the x is e to the x, but based on what we just did last class, this felt like the most appropriate and smooth way to sort of transition into talking about e and other exponential functions. So let's talk about derivatives of exponential functions with bases that are not just e. In the 5.0 notes and video, we showed that b to the power of x is equal to e to the x natural log of b. And you can go back and look at those notes or the video to verify that to yourself again. But what we're going to use now is the idea of using the chain rule and the change of base formula, and also using logarithmic differentiation to figure out, okay, if I know that b to the x is the same thing as e to the x natural log of b, can I use that information to find the derivative of an exponential function, something to the power of a variable? All right, so let's look at this function and let's take the derivative of both sides with respect to x. So that's going to give me the derivative with respect to x of b to the x, which is the whole thing that I want to figure out. How do I take the derivative of something like b to the x, times the derivative with respect to x of e to the x natural log of b. Now, we just learned how to take the derivative of e to the power of x. We are going to have to apply the chain rule here because this exponent is a function that has a derivative as well. So what we're going to see is that the derivative of e to the x natural log of x, so the derivative of x natural log of b, sorry, not x natural log of x, the derivative of x natural log of b is going to be just natural log of b, and the derivative of e is just e to whatever it already was, so e to the x natural log of b. So this is still the derivative with respect to x of b to the x. But we can actually simplify this more because e to the power of x natural log of b is just b to the x. It was defined that way at the beginning. So we can say that the derivative with respect to x of b to the x is equal to the natural log of b times the quantity b to the power of x. Now there's another way that we can prove that this is true. We can prove it with what we've been using for a couple of days. We've been using logarithmic differentiation. So let's start with y equals b to the x instead, and then let's natural log both sides. Natural log of y equals x natural log of b. Now we can differentiate both sides with respect to x. So 1 over y dy dx equals natural log of b. We can multiply both sides by y, and I'm going to do that direct substitution step here as well. So we know that y at the beginning of this problem was equal to b to the x. So y equals b to the x. So when I multiply both sides by y, I'm multiplying both sides by b to the x. So again, the derivative with respect to x of b to the x is b to the x times the quantity, or times natural log of b. So the natural log of the base times the original function b to the x. So what you're going to see down here in this summary, the derivative of e to the x is e to the x. The derivative of e to the u, meaning that we maybe have some function that we need to apply the chain rule to. So this one is in terms of using the chain rule. Make sure you take the derivative of the exponent and multiply that by e to the same exponent. The derivative of b to the x is natural log of b times b to the x. And then again, remember, this is also our chain rule. Anytime you see u, it's adding in that chain rule version. The derivative of the exponent times natural log of b times b to the power of u. So let's look at a few practice problems here. On number 1, we have e to the power of something. So when we take the derivative, dy dx, we're going to take the derivative of that exponent. So we're applying the chain rule. The derivative of that exponent is 4x. And then e, the derivative of e is e, so e to the 2x squared minus 1. On number 2, we're going to use the product rule and the chain rule. So dy dx is going to equal e to the 2x if I take the derivative of x and multiply it by e to the 2x, plus keep x there and multiply x by the derivative of e to the 2x, which is just 2x e to the 2x. So this is going to be, you can't really read that, so I'm going to try and rewrite it. E to the x, here, let's just factor 1 out. That'll save me some space. E to the 2x times the quantity 1 plus 2x. You could leave it this way as well. So that would be 2x. Here, let's try and just rewrite this. This would be x times 2, so 2x e to the 2x. So you could leave it as the top, or you could factor e to the 2x out and use the bottom one. For number 3, f prime of x is going to equal, so based, I'm using this over here, is going to be the natural log of the base, which is natural log of 3, and I'm going to multiply that by the original function, 3 to the natural log of x, and I'm going to multiply that by the derivative of the exponent, which is 1 over x. So I guess if we wanted to make this look a little bit more concise, we could say natural log of 3 over x times 3 to the natural log of x. Okay, number 4, the first thing you should do on this problem is use properties of exponents. Go back to your Algebra 1 brain and change this. This is really the same thing as just saying 12 to the power of x. So g prime of x is going to be the natural log of 12 times 12 to the power of x. So these properties in this green table you need to know, and you need to know how to use them. Let's look at a couple of examples that tie this back to previous chapters. So find all of the relative extrema, list the answers as ordered pairs, and then notice that number 6 is using the same function, but now we're going to talk about inflection points. So we're going to work with the first derivative on number 5 and the second derivative on number 6. Go ahead and pause the video and find the first derivative and look for those relative extrema. So here's our first derivative, e to the negative 2x squared minus 4x squared, e to the negative 2x squared. So you don't have to simplify this at all, but for me, when I'm trying to figure out where this is undefined or 0, this is going to be much easier to look at if I factor out e to the negative 2x squared. Now, no matter what I do, this e term is always going to be positive, and it's never going to be 0. So I just need to figure out for my critical numbers what makes 1 minus 4x squared, what makes that equal to 0. And that's going to be plus or minus 1/2. So I'm going to make my number line. That's going to lead me to a relative max at 1/2, 1 over 2 root e. since f prime changes from positive to negative, and a relative min at negative 1/2 negative 1 over 2 root e, since f prime changes from negative to positive. For number 6, you're just going to find the second derivative and then find your possible points of inflection there. So go ahead and pause the video and do that. So there's our second derivative. Something I want you to notice is that we do have some like terms that we can combine. That would give us negative 12 x e to the negative 2x squared. And then if after we combine those, we can actually factor out negative 4x e to the negative 2x squared. And that would leave us with 3 minus 4x squared. So our possible points of inflection here are at 0 and plus or minus root 3 over 2. So make a number line with those. Each of those is going to be a point of inflection. So we have inflection points, and these are true because f double prime changes sign. And those are going to be at 0, 0, negative root 3 over 2, 0.193, and you could use a calculator to find that. Root 3 over 2, sorry, this should be negative also. Root 3 over 2, positive 0.193. And then the last question before we get into something new is the end behavior. This is just recapping, reminding you that when you're thinking about the end behavior, you can look at the limit as x approaches infinity and the limit as x approaches negative infinity. So looking at this of x over e to the 2x squared, that limit is going to be equal to 0. Since the denominator is growing much faster than the numerator, the denominator is growing exponentially. And then similarly here, same story, it's getting smaller. It's still changing exponentially. The bottom is growing faster than the top. So this has a limit that's equal to 0, which means that the end behavior is that we have a horizontal asymptote at y equals 0. So now we're going to look at integration. We talked about differentiation. Now we're going to move over and talk about integration. So thinking about integration as the antiderivative, or the opposite of differentiating, this first one should make complete sense. The integral of e to the x is e to the x plus some arbitrary constant c. If we are looking at b to the x, so remember that we could change this to be the integral of e to the x natural log of b dx. And if we integrate this, think about the chain rule here. This would give us 1 over natural log of b times e to the x natural log of b. And something else I want you to notice is that you may have to use u substitution for you to sort of follow this process, that you would let u equal x natural log of b. So du would equal natural log of b dx, and you would simplify that through. And then to finish this off here, this is the same thing as 1 over natural log of b times b to the x, because e to the natural log of b is b to the power of x. So here in this summary box, we have the integration rules that we need for involving exponential functions. So the integral of e to the x is e to the x plus c. If the exponent is a function, then you're going to use the chain rule. That's what that second one with u is saying. Or you're going to use u substitution to undo the chain rule. And then the third one, if you're using some other base, that's going to be 1 over the natural log of that base times b to the power of x plus a constant. And again, if that exponent is a function, make sure that you integrate that function as well. So that's where the u substitution version comes in. Now let's look at some practice problems. So on number 8, I could do this simply by reversing the chain rule. And if you see that, because the derivative of that exponent, x squared minus 1, that derivative is 2x. If you see that, go ahead and do it that way. But since this is our first time really practicing integrating with exponential functions, I'm going to do the full u substitution on this problem. So I'm going to let u equal x squared minus 1. So du equals 2x dx. And I'm going to change the bounds of this integral since it is a definite integral and it has bounds. If x is 0, u is negative 1. If x is 1/2, 1/2 squared minus 1, then I get negative 3/4. So this is going to become the integral from negative 1 to negative 3/4 of x times 4 to the power of u times du over 2x. So these x's are going to go away. I'm going to take 1/2 out. Negative 1 to negative 3/4 of 4 to the u du. So that's going to give me 1/2 times the integral of 4 to the power of u is going to be 1 over natural log of 4 times 4 to the u. And this is going to be evaluated from negative 1 to negative 3/4. So I'm going to leave this as 1/2 times, actually, let's write this as 1 over 2 natural log of 4 times 4 to the negative 3/4 minus 4 to the negative 1st. And I'm just going to stop right there. And since this is a definite integral and it has bounds, we do not have to worry about plus c. Looking at 9 and 10, we are going to have to make sure we have a plus c because those are indefinite integrals and they do not have bounds. So let's look at number 9. Again, I'm going to use u substitution. I'm going to let u equal 2x to the negative 1, which is the same thing as 2 over x. That means that du is going to equal negative 2x to the negative 2nd power dx, which means that dx is going to equal du times x squared over negative 2. So I'm going to rewrite this integral now. The integral of e to the u over 3x squared times my u substitution is giving me du x squared over negative 2. So these x squareds are going to divide out. I have a negative 2 and a positive 3 in the denominator, so I'm going to take 1/6 out. 1/6 times the integral of e to the u du, which is just going to be 1/6 times e to the u plus c, except let's substitute back in what u is. U is negative 2x to the negative 1st plus c. Okay, number 10. This looks really complicated, but what I want to do is I know I'm going to need to use u substitution. I'm going to look at the function that has the most going on, and I'm going to let u equal that. So I'm going to let u equal the thing in the denominator so that my goal is to have u to the 4th. So let's let u equal e to the x plus e to the negative x. That means that du is going to be e to the x minus e to the negative x dx, which means to solve for dx, I'm going to get du over e to the x minus e to the negative x. So let's substitute all of that into our integral. So all of these leftover e to the x's, they're going to divide out. We're going to end up with the integral of u to the negative 4th power du. This is not some special exponential function. We can just use the power rule on. This is going to be negative u to the negative 3rd over 3 plus c, and then we need to substitute back in what u was, so negative e to the x plus e to the negative x to the negative 3rd power over 3 plus c. Now the last thing I want to do in this section of notes is I want to tie all of this exponential natural log idea back to Unit 4 a little bit and talk about area bounded by curves, but now involving exponential functions. And then lastly, we're just going to talk briefly about how to deal with arc length in calculus. So let's start by working on 11 and 12. So go ahead on number 11 and number 12, quickly just sketch those curves that are being described. Now to find the area bounded by each of those curves, we know we need to set up the integral. So looking at 11, this is going to be the integral, and looking at our x values, we're going from 0 to natural log of 4 of, natural log of 4 of e to the x dx. Well, that's just going to give me e to the x evaluated from 0 to natural log of 4, which is going to give me e to the natural log of 4 minus e to the 0, which is going to be 4 minus 1, which is going to be 3. On number 12, we're going to be integrating from 0 to the square root of 6. and we're going to be integrating x times e to the negative x squared over 4 with respect to x. You can reverse the chain rule here, but again, since this is kind of new and I know some of you aren't that comfortable with that, I'm going to use u substitution. So I'm going to let u equal negative x squared over 4, which means that du is going to be negative 2x over 4, or negative x over 2 dx. So when, I'm going to just keep going down this way, when I fix this, what I'm really going to be saying is my integral of x times e to the u times du. If I solved this for dx, I would get negative 2 in the numerator and x in the denominator. Let's look at our bounds. If x is 0, u is still 0. If x is the square root of 6, then u is going to be negative 3 over 2. I can simplify these x's here. I'm also going to switch this integral around to make it have negative 3 over 2 in the bottom. But notice when I take this negative 2 out, negative 2 times this negative for changing the sign, this is just going to become 2 times the integral of e to the u du, which is going to be 2e to the u evaluated from negative 3 over 2 to 0, which is going to be 2. If I plug in 0, e to the 0 is 1. So 2 minus 2e to the negative 3 over 2. The very last thing we're just briefly going to talk about today is how to manage arc length in calculus. And the beautiful thing is it's really just a formula. It is a formula that you should know, but it's not an incredibly challenging formula to work with. You're going to use a calculator to find the arc length of this curve on the given interval of 0 to 2. So here's the formula. You're going to take the integral from the bound, so 0 to 2, of the square root of 1 plus the derivative. So let's look, f prime of x here is just going to be 9x squared minus 3. So of 9x squared minus 3 squared. So the integral from a to b of the square root of 1 plus the derivative squared, and you're integrating with respect to x. So this particular problem, if you needed to, you could expand this out, but I still think that as of right now, we don't know how to integrate something like this. So this is sort of on your calculator. Substituting that in, this would give you 20.633 as the length of the arc over that interval. So this formula could come up. Obviously, you're going to see the words arc length in the problem if you are being asked to use it, but I just wanted to mention it here. It ties a little bit back into Unit 4. So, important things to remember for this section: how to differentiate using exponential functions, the fact that the derivative of e to the x is e to the x, and the integral of e to the x is e to the x plus c. Making sure that you know how to integrate exponential functions that are not of base e and how to differentiate those functions as well. And last but not least, tying this into arc length and finding the area between two curves now involving more complicated functions that maybe involve e. So I look forward to supporting you on this in class and answering your questions. Thanks for listening.